aim fluid, other internal fluid, skin temperature, metabolic effect, and pressure drop or other tissue necrosis. I think many people see this picture, the skin necrosis. Many research try to understand the tissue damage. I think most popular one is to measure the skin blood circulation, because most people believe pressure sore caused by lack of blood circulation. If some area, for example, if you sit there for a long time, the blood circulation will be blocked. If keep this situation for a long time, the tissue will be not problem. So we can use the Doppler flow meter to measure the skin blood flow. I did that long time ago when doing my PhD study. So I try to understand how the blood circulation affected by either normal force or shear force. When I talk about normal force, shear force in terms of the skin surface, I apply normal force to skin surface, increase gradually. I found the reading from the laser Doppler will reduce gradually. At the same time, if I keep the normal force constant, I increase the shear force, then you can see increase sharply, then gradually reduce with the load increase. Anytime when you apply the load, the reading will sharp increase. This is the interfere. If some interfere by the equipment, it will have some sensitive to some change. Okay? But anyway, when you after a few seconds, that is stable. We can see the trend with the load increase of shear. The blood circulation also reduced. Okay, so if we combine the two together, we can find the resulting force applied on the skin surface effect on the blood flow reduction, and we can use the linear regression to understand that. Now, go back to footwear design. As an engineer, we always want to say whether we can design some optimized shoe. We using parametric study, we often list what other major factor may affect on the design. So if I list it here, okay, the design or the factor affecting our footwear should be internal structure, foot structure, bone, joints, muscle, ligaments, soft tissue. The shoe structure, the shoe design includes insole, midsole, outsole, coverage, and the heel support. Includes the shape, size, and the material. All those related to shoe design. This related to internal foot. Then form different interface, plantar interface, foot cover interface, outsole support interface. Most people do measurement work on this interface. Then foot have a biomechanical environment, include pressure distribution, shear stress, friction, slip. And we talked with the professor. So many people interested to measure shear, measure friction, even slip. But we don't have the means. We do need some transducer to do that. We got the transducer under your team support to measure the shear. For slip, we try some sensor like the moss and put the moss to the shoe. We do get some information, but not stable. And if we can use the technique to do that, I'm sure friction slip is another very important parameter for people to design shoe, because this will cause heat, cause energy loss. Impact, vibration, temperature, heat transmission, humidity, all those are environment for foot. Outcome, I think, like you present, there are different outcomes. You may check working style, feet or comfort, ankle protection, and stimulation, skin damage or adaptation, knee alignment. Many presentations talk about the knee load and functional activity. All those can be outcome. So I list this. I want to say different people, different situation may need different design. So no uniform design criteria. We have to consider all those parameters to state what you want. And I also want to say, when you design any experiment, you should know all those parameters. You should have a prediction. And if you do something, for example, you change the arch support, you want to see how the knee loading change. Maybe that's not a major effect. Then your experiment cannot give you satisfactory answer. And so anyway, anytime when you design, you should have a prediction first. And if you know all those effects. Now, in talk about interfacial biomechanics, actually my team mainly work on those called interfacial biomechanics related research, include quantifying material property. We need to know what the tissue property in vivo or in vitro. We can cut a piece of cadaver tissue to measure the mechanical property. Our team also designed an ultrasound measurement system to get the tissue property in vivo. That means on foot. What are the cushion material property, skin frictional property, is related to material property. Also have a big research team related to quantifying interface condition. Those include pressure distribution, many research on that. I think if you only measure pressure distribution at this date, very difficult to publish your result in ICI journal. Shear stress and measurement. We did some, but we do need some better transducer. Sleeping, temperature, humidity, and differentiate that condition and activity. Now, the third part includes the tissue response to mechanical loading, internal stress strain distribution, pain-tolerant region ability, blood circulation under mechanical loading, or tissue damage under loading. And all those, we call that interfacial biomechanics. We can do that experimentally. Our team also do computational. Okay, and we do the high heel shoe, we do the kinetic study. I'll give you some example. And we using the transducer, tri-axis transducer, and develop in angiography. And this tri-axis transducer can give the normal force shear in two directions in terms of measurement surface. So when we talk about shear, we should say always which surface. Okay? And this is the parameter for the transducer system, 75 Newton for shear, 200 Newton for normal. And this is enough for working, but too small for other sports activity. So the sensor has a 15 millimeter, 17 millimeter on top, and 10 millimeter thickness. Then we fit, these are the parameters. We fit that into the high heel shoe for 5 regions. And this is the transducer fixation. We try to reduce the interface of transducer. We cut a piece of insole material, put on the top, glue on the top. Okay. Then we try to simulate the original situation. However, we put a metal material here, it will change the real situation. If we can design something with the same stiffness, but I know it's not easy. The result gives some balance that this is a balance standing, that means double limb standing. We can see what are the shear direction, and we can see what are the heel height effect with the 3 different heel height, 40, 50, and 70 millimeter. Then we can see what are the resulting shear maximum. Pressure heel standing for 5 regions. This is the result during working for the 5 regions. And I don't want to present in detail how big of the results. Okay, anyway, you can see the pressure, AP shear, ML shear. And this slide try to give you better understand for different phase. And as this is a different location, this is a stance phase. You can see what are the shear direction. You can see the length represent the magnitude of the shear, and this represents the normal pressure for 3 phase and the different location. Okay, and this slide try to summarize what are the resultant force for different heel height and for different only 2 heel height here. you can see how the heel height affect on the peak pressure on the resulting shell. Same thing, okay, these are all the data. Okay, this also talk about the working speed. If you change the speed, how the pressure and the shear strength change. That's why I say speed is another important factor. If you don't control speed, and all the contact will change. Now, we have done a lot of other related studies, including cadaveric study and some modeling. I will give a more detail later. And the cadaveric study, we try to using cadaveric foot to understand the foot mechanical property. And I try to use that to show the importance of the muscle control for your model. If you don't give the muscle force, only give the bone force, foot is not stable. And we put some transducer here to measure the strain, the marker to see the bone rotation, then some force for the muscle. And also work with using the K-scan, put it into the joint. I think all those pressure measurements are seen to many other researchers here. And we talk about the heel height effect. Try to remove other parameter effect. We only change the heel height and remove other things. And to see how the heel height affect on the pressure distribution. And we also made some mold. Try to see how the length, width, or the shape of the last affect on plantar pressure distribution. The proper A, we only try to see one parameter effect. And also we did some experiment for the base, the height, and where the base and the different change of the shoe design, the base size, the alignment for knee using the wedge. Okay, I think this is very similar to what you present today. And this study we published and try to understand people using foot shape to make the insole, then to see how the insole reduce the peak pressure. Okay, we did this study a few years ago using different cast position, no load, half body weight, full body weight. Then we get three shapes of the plantar foot. Then we're using this to make the insole to ask people to wear, then to working to see